Bismillahirrahmanirrahim. Ladies and gentlemen, welcome to the online workshop on machine learning, level 2. So I'm Dr. Saleha Naghmi Habibullah. I'm a professor of statistics at Connect College for Women in Lahore in Pakistan. And also at this time, I'm rendering services as honorary director of PISTAR, the Pak Institute of Statistical Training and Research, which is very intimately linked with ISOS, the Islamic Countries Society of Statistical Sciences, both of which were founded by my teacher, my mentor, Professor Dr. Munir Ahmed Marhoom. All right, the PISTAR team consists of the following persons. First and foremost, I would like to mention Mr. Mohammad Iftikhar, who is well known to many of us. He is the executive secretary of ISOS, and we, the PISTAR people, now consider him, actually we've considered him an integral part of the PISTAR team from the very beginning, but today we are putting his name here on the top because of all that he does for us. Professor Muhammad Aslam, retired from FC College, where he was head of the statistics department for a very, very long period of time and served tremendously. Dr. Sharka Hashmi, assistant professor at Lahore College for Women University, Lahore, an integral part of the PISTAR team. Ms. Saleha Mishkoor, lecturer at Minhaj University, Lahore. Ms. Kamal Aslam, who has graduated from Connect College. She has completed her MPhil in statistics. Ms. Aqsa Abid, our youngest team member, she has completed her BSc honors in statistics from Connect College, Lahore. The focal person is well known to every single one of you. This is Dr. Syed Wasim Abbas, who was just now asked to start, let me know when to start the recording. He's assistant director at the Bureau of Statistics, Punjab. And he does a tremendous amount of work for the smooth running of these workshops and for the organization. All right, ladies and gentlemen, what is the plan for today? After the few words of welcome, I'm going to hand over to, it says Ms. Kamal Aslam, but due to some reason, she's unable to be here. So Ms. Aqsa Abid, who will then present his CV, and then she will also present the resume of Dr. Alireza, subsequent to which both of them will begin this second workshop on machine learning. The first one, as you know, many of you know, happened on the 15th of November, 2020. At about 3:25 sharp, we will have a short break. And in Pakistan, that will be the time for Asad prayer. And after 7 minutes, we will resume. And at 3:32, Dr. Reza and Dr. Alireza, they resume the workshop on machine learning. At 4:12, we introduce, it says that I'm going to do it. I have requested Dr. Sharka to do it, to present the resume of Associate Professor Aisha Bilgin, who is from Australia. She's Associate Professor at the Macquarie University in Australia. She's the keynote speaker for today, and she will be presenting her keynote address, Machine Learning Applications for Health Problems. Subsequent to her half an hour long keynote speech, we will have a question answer session. And I hope that you people will have a lot of questions to ask, subsequent to which Iftikhar Sahib will present the vote of thanks, after which we will be closing this workshop. So without further anything else, the very first thing, who are the participants from Pakistan for today's workshop? Ms. Baliga Yunus, Dr. Kulsoom Akhtar Chaudhry, Mr. Muhammad Riaz, Dr. Shakila Bashir, Dr. Itrat Batul Naqvi, Dr. Iram Salim, Ms. Safura Samuel, Ms. Shafqat Parveen, Mr. Mustansar Itazaz Amjad, Ms. Amber Zaki, Mr. Abdul Tawwab, Ms. Fiza Chaudhry, Mr. Mirza Kalimullah, Mr. Muhammad Abdul Salam, Mr. Mustafa Nadimi, Ms. Uzma Maqsood. I do want to say that if some people have already completed their PhDs and I'm unaware of it, please excuse me for that and do let us know so that next time we write doctor instead of Mr. or Ms. Um, and also, of course, we have Ms. Aisha Sultan, Ms. Mehnaz Makhdoom, Mr. Muhammad Waqas, Dr. Azia Noreen, Ms. Aruba Siddiqui, Ms. Salvina, Mr. Muhammad Suhail, Ms. Rahila Hafiz. We have international participants, Dr. Waqas Sami, Dr. Najla Muhammad Karmala. They are both in Saudi Arabia, Ms. Nadia Rahman and Mr. Yasir Rahman from Canada, Dr. Aslam Grunlu Alma. I hope I'm pronouncing your name correctly, Aslam. And please excuse me if I'm not. From Turkey, we are delighted to have all of you, just as we are delighted to have every single other person. Mr. Farhan Farouk from Denmark and Mr. Mavora Thomas Makudisa from Kenya, our perpetual participant, because he's been with us, I think, from the very, very first one. Okay, now I request my dear student, Aqsa, to present the resume of Dr. Reza. Aqsa, would you want to do the slides or do you want me to do them? Is it all right if I keep doing it?
Ma'am, please, you can do it for me.
Okay, all right. So you can start.
Dr. Reza, Arabi, Department of Mathematics and Statistics, postdoctoral fellowship at Statistics with working with Dr. Abdul Qadir Hussain at University of Windsor, Ontario, Canada. Next, please. Educational background. Postdoctoral fellowship in Statistics, Department of Mathematics and Statistics, University of Windsor, Ontario, Canada, 2020 to present. Postdoctoral fellowship in Statistics, Predictive Modeling, including Big Data Analysis, MC Masters, University, Hamilton, Ontario, Canada, 2019 to 2020, July. He is visiting scholar for the PhD Award, Statistics, MC Masters, University, Hamilton, Ontario, Canada, 2013. PhD in Statistics, Statistical Inference, Firdausi University of Mashhad, Iran at 2015. MSc in Statistics, University of Tehran, Iran from 2006 to 2008. BA Statistics, University of Tabriz, Iran from 2003 to 3. University and appointment. Seasonal faculty, Department of Mathematics and Statistics, MC Masters, University, Canada from 2018 to September to December. Assistant Professor of Statistics, Department of Statistics, Faculty of Mathematics Sciences, University of Tabriz, Iran, 2014 to present. Research area: shrinkage estimation, machine learning, biostatistics, high dimensional data analysis. He published 30 papers, supervised 6 master students and 3 PhD students. Experience with machine learning, developed clinical risk prediction models to predict preterm births in Canada. Preterm birth accounts for nearly 2/3 of infant deaths in Canada and is associated with increased morbidity throughout the life course and subsequent adult onset chronic disease. In addition to these health effects, preterm birth in Canada places $560 million annual on the society in terms of healthcare and education. Dr. Reza has analyzed a very large scale and complicated data sets from bond database. He has developed clinical risk prediction models using machine learning algorithm to predict preterm birth in Canada with 80% AUC. The data he used was Hall of Birth in Ontario for 2 years. Using machine learning, Dr. Reza has successfully explored the main risk factor of preterm births in Canada, and now the practitioners can benefit from those models to provide treatment for their patients and prevent the issue. Outcome will advance the knowledge in the field, help disease pattern birth by developing possible interventions, and will save enormous amount of direct and indirect cost in Canada. Dr. Reza has developed 3 papers as the main author and submitted to British Journal of Obstetrics and Gynecology, American Journal of Obstetrics and Gynecology, and Obstetric and Gynecology Journal.
Thank you so much. And the next one is the introduction of Dr. Alireza.
Dr. Alireza Safariyan, Department of Mathematics, Assistant Professor of Statistics, Faculty of Mathematical Sciences at Allama Tabatabai University, Tehran, Iran. Educational background: visiting scholar for the PhD Award, Statistics, University of Manitoba, Winnipeg, Ontario, Canada, 2018. PhD in Statistics, Statistical Inference, Shahrud University of Technology, Shahrud, Iran, 2019. MSc in Statistics, Tabriz University, Tabriz, Iran, 2007 to 2009. BA Statistics, University of Tabriz, Tabriz, Iran, 2002 to 2006. University appointments: Assistant Professor of Statistics, Department of Statistics, Faculty of Mathematical Sciences, Allama Tabatabai University, Tehran, Iran, in 2020 to present. Assistant Professor of Statistics, Department of Statistics, Faculty of Mathematical Sciences, Shahrud University of Technology, Shahrud, Iran, 2016 to 19. Assistant Professor of Statistics, Department of Statistics, Faculty of Mathematical Sciences, Payam-e Noor, Tabriz, Iran, 2009 to 2015. Research areas: shrinkage estimation, machine learning, network data analysis, reliability, high dimensional data analysis. 6 published paper, advisor to master student. Experience with machine learning, estimating certain centrality parameters of networks using innovative network sampling approaches on Facebook and Google Plus data. Dr. Alireza and team was able to develop necessary basic theoretical results associated with forest fire sampling for estimating network parameters and investigate the suitability of judgment of post-stratification and ranked set sampling design in estimating network centrality measures. They then compared their results with commonly used method in this context. Their preliminary investigation has revealed a few interesting projects for future research in this direction. Next, please. For example, the team hopes that they will be able to develop a non-parametric model using spline method for estimating inclusion probabilities associated with forest fire sampling from a network. This is very important problem and will help to develop more efficient design-based estimator of network parameters, and it opens the venue for further progress on network parameter estimation using rank-based sampling designs.
All right, thank you so much, Aksa. Thanks for that. Ladies and gentlemen, I would now like to request Dr. Reza and Dr. Alireza to begin the workshop. And Dr. Reza, I think I should stop sharing the screen, and you would like to share it from your side, is that right?
Yeah, thank you. So,
all right, okay.
Thank you, Dr.
Oh, I
Saleha.
also, sorry, I do want to say one more thing. I'm so sorry. I want to acknowledge the presence of Dr. Ali Hadi, Professor Ali Hadi, who's from the American University in Cairo. He was one of our invited speakers at the World Statistics Day program. And more importantly, he has been the president of the Islamic Country Society of Statistical Sciences. I'm delighted to have you, Dr. Ali Hadi, Professor Ali Hadi. And also, I want to welcome Associate Professor Aisha Bilgin. Thank you for joining. Your talk is towards the end of the workshop, but I'm so grateful to you for joining just now. This is great. Ladies and gentlemen, I've already told you that we will be having Aisha speaking with us on the application of machine learning in health problems. So if I'm missing anybody else, I want to request that please forgive me. Every single one of you, you have taken time to be here. Thank you so much. All right, over to you, Dr. Reza.
So thank you very much again, Dr. Saleha. We are so much delighted to handle the second workshop on machine learning algorithms. So I welcome all of you from the University of Tabriz from Iran in the northwest of the Iran, close to Turkey border, a nice area. So I would like to thank you again, and also thanks Professor Ali Akbar Heydari, head of the Department of Statistics, who participated at this workshop. And I would like also to thank all of, I would like to thank Dr. Neda Gilani, who is Assistant Professor of Biostatistics from the University of Tabriz Medical Park, who is also attending at this workshop, and welcome to all of the other people. So my apologies if I miss. Yeah, we are going to start the second session on the machine learning algorithms. And so we are going to develop those things in this session. So let me share my screen with you. And then, so what we are going to cover in this session is, like, briefly, I'll go through again with the machine learning part. And then I will cover in this session decision trees, random forest, boosting methods, linear support vector machine, SVM, along with nonlinear model. And at the end, we go through the linear regression model. So,
Dr. Raza, I want to interrupt here. I just want you to know that we in Pakistan, many of us, including me, you know, we don't know these concepts. So you will need to do it from A, B, C.
Yeah, definitely.
And we want to learn something a little bit. But,
yeah,
you know, I'm trying to, you know, say what everybody else is wanting to say. You know, that we are kind of, we are looking forward to learning a little bit about it. And I think we need to get to do it right from the very ABC.
Yeah, definitely.
Thank
I will try to. Yeah, I will try to do my, you know, very basic, in fact, this figures, and so show you how we can develop and what those methods are, in fact. So I think this session will be better than the previous one. So we will cover these things, so with both explanations and along with our codes. So let me just begin with the simple things with the learning approach. So what is the learning? So learning is something that we are getting knowledge from the previous examples or any experience, and then we are updating us to the new things, and if something new happened, then we can predict. So the stuff are machine learning. The all things that we are trying to do is called like prediction. So we want to predict. So we want to predict based on what we have learned so far. And this is obviously something that here we need to mention, that we need a lot of experience to be like a super learner. I mean, in terms of, you know, predicting very accurate models. So let's start with this figure. So we see some apples in the first row. Second is their peach, and like tomatoes, cow, and dogs, etc., horse. And now if somebody gives like the figure here and asks what this, we will say immediately this is an apple. So here we learn from the figure of apples, so what does it look like, or from the peaches and etc. So this is the things that we, in fact, we call in the machine learning term as a classification. So we mostly want to classify the things to, you know, based on from our previous experiences. So this is the main, so one of the objective of machine learning. And I mentioned there are several methods. One is called classification or supervised learning. Another one is unsupervised learning. So we go through unsupervised learning in the next workshop. So, but today our focus is mostly going to be for classification. So as I mentioned in the previous session, we need to, in fact, to be very careful when developing any machine learning algorithms. So for now, please don't be like interrupted if I say some of the theory of machine learning, because they are super important for us. So we need to have, firstly, we need to have the data. So we need to have like we need to pre-process the data. We need to work for the missing in the data. So now how we can like treat the missing data if they are. So we can use several methods. One is called, you know, imputation. Another is called like maybe deleting the missing observation and just work with the, in fact, complete case analysis. So we need to have a data matrix like here. So we see here, for example, x1, x2, little x1, x2, etc. So let me just magnify my page, and then, yeah, hopefully this time it is better. So, sorry. Yeah, so then we need to, for any of those machine learning algorithms that I am going to talk, even today or like in the future, we need to find something called hyperparameter. We need to optimize those hyperparameters. Then we need to fit the machine learning in the training data. We need to fit the best model. We need to find the best model in the trained data. And then we need to evaluate those techniques in the testing data. So if we miss any of these steps, we cannot say that, you know, we developed the machine learning algorithms. And in fact, recently, you know, there are many papers withdraw or rejected because failing, you know, any step of this machine learning development algorithm steps. So we need to be very careful. So keep in mind that, you know, we need to have all those four, in fact, approaches properly done, so that we can say we developed a machine learning method. So I will show you how to do them like very carefully. So for number 4, how we can evaluate the data. So we have some measure of accuracy called AUC, classification accuracy, sensitivity, specificity, PPV, and NPV. So I'll tell you what they are. So accuracy is the correct classification rate. So for example, if I have like, if I correctly classify 10% of the data, I will say the accuracy is 10%. If I correctly classified 90% of the data, then I would say my accuracy is 90%. So we have something that what is important is true positive rate. True positive rate is very important, especially for predicting of the disease, and also negative predictive value. These are very important part. So we want to see how the actual values are in fact coincide with the predicted values. So we need to have this matrix. This is called confusion matrix. So, and in fact, let me introduce this paper, especially for those who want to work on the application of machine learning for the medical science. So a new guideline published in BMC in medicine recently in 2015, and they in fact they revealed this, in fact, 17 steps how we can develop, how we can predict, and how we can report a transparent multivariable prediction model, specifically for machine learning algorithm. Because I will show you, like maybe in this session or next session, that it can be easily, you know, misleading if we don't take care of those, you know, steps. Now I am going to show you what those basic machine learning algorithms from scratch. So I am opening my paint. So if you don't see my paint, then let me know, please. So I'm going to start with some simple example. So let's say I do have age here. right? So in my x-axis, I have age, and in y-axis, this is 0, 1. I have some outcome. Let's say this is cancerous or non-cancerous. So for cancer, I will put maybe some, some circle, like for non-cancer. And then for cancer, I will put some, like red triangular. So let's suppose I do have this data, right? So again, I do have some circle here, and let's say I do have some triangular here. So this is my data, right? So we have a bunch of 0 and 1. Now somebody asked, okay, do a model and tell me, so if somebody at this age, let's say this is 55, and tell me what will happen in 55, because I don't have the observations here, right? So we are going to predict whether or not in 55 it will be 0 or 1, or the guy will have cancer or non-cancer. So at first I'm just looking at age, or it can be like any continuous variable or discrete variable, like gene expression. So maybe instead of age, we can say this is a gene expression. So somebody will tell us, okay, if the guy is coming with 55 age, and maybe he comes with many other variables like blood pressure or blood type or anything. So we want to predict. So if the guy comes with 55 years, whether or not he is going to develop a cancer, I mean a circle, or a rectangular, right? So this is my question. And in fact, the whole things is going to predict the outcome for this guy with very, like as much as precisely. So now what we talked, in fact, so the data I think is clear, right? So we have some non-cancerous, but some cancerous people here, there are some overlap. On the other hand, there are some overlaps here. And it seems that, it's a mixed. So and now if we want to predict here, or if we want to predict somebody here, or even if I want to predict somebody here, so what's going on to be this guy? So if I am going to predict here, like in this age, so let's say I'm going to predict, the event for this guy of, let's say this is 59 years old. So if you remember, we talked something about k-nearest neighborhood, right? So what the k-nearest neighborhood was, in fact, from our previous session, okay, I will look at this neighborhood of 59, then I will count how many cases available here. So I do have 6. So 3 of them are cancerous, 3 of them are non-cancerous. So making a decision here is so much hard. But if the number of, let's say, cancerous are I mean, if we have more of triangular, then I could classify that this guy as a red. So because I say that the frequency of red are much higher than the frequency of the circles. So that's kind of classification based on k nearest neighborhood. Now, for the k nearest neighborhood that we discussed from last week, so the name was k nearest neighborhood, or I can simply write k and n. So how many k I should specify when I have a big data? So my data here is quite few. I have only one variable. So, but if I come to maybe like 30,000 variable with 1 billion data sets, so what can I do? So for this k, that in fact I mentioned to you how we can build a machine learning model. So for this k, we need to use cross-validation. So sorry, we need to use cross-validation to find firstly what the value of k, and so if it is 1 or 2 or 3. So the cross-validation will tell us that how many, in fact, which k is suitable for our data. So now this is the nature of, like k and n. So I'm going to draw the picture again here and show what is the logistic regression. So we had a bunch of circle here, and so here. So let's say I have some, triangulars here. So now I mentioned that if we go through if we want, so let's say this is like my, like any predictor variable x, and this is the outcome is 0 or 1. So here is 0 or 1. Now, if we want to fit a logistic regression is going to fit a line like this so that it can predict the probabilities. Now, if we fit, then we see that there are some people here, they will mix. So here we have both triangulars and also circles. So we also have the same issue here. So it means that logistic regression cannot work. Now, what we can do, we can use something called the decision. So we can use something called support vector machine here. So what the support vector machine will tell us, the support vector machine will tell us that we can build like an area like this for the blue, and we can develop an area like this for the red ones, right? So let me write. So we can develop an area like this, and whenever any observations, like any X happens in this area, I can predict as this guy or this guy. Whenever my X is falling in this area, I can go through. But let me be more accurate with the support vector machine. So how it works? So if I do have the data like this, so I have some red here, and I do have some other observations like here. So blues, sorry. So I do have blues here. So let's say these are one group of patients, so who have some certain disease, maybe cancer, and this guy has no cancer, right? So I am going to write in 2 dimensions. So this is x1, one variable. This is x2, another variable, and these are the my outcomes. So I do have 2 non-cancer and 3 cancer. Now I want to build a prediction model so that it can really classify my cases into cancerous and non-cancerous. So if I do, definitely logistic regression cannot work for this data, because logistic regression will fit, like this line, and it will not be okay. So what we can do, I can divide my area into 2 parts like this, and I would say, okay, if X is less than this guy, okay, then classify the people for this for non-cancer. If X1 is bigger than this guy, here, let's say this is 10. If X1 is bigger than 10, then I would classify them as as blue. So there is an issue, right? So we see there might be some misclassification, because some of the red part will go to blue, and some of the blue part will go to the red. So which in fact is not so much good. So what the support vector machine, so in fact, the job of partitioning the space is related to something we call as decision tree. So decision tree works when we have the data like this. So if my data is like this, so let's say I do have some circle here in the 2 dimension, x1 and x2. I do have some circle here. I do have some other, rectangular here. So rectangular and then circle. So let me draw some circle here. So what I can do, I can split this area into 4 parts. 1 part. So this 4 part, partition number 1. So I can say A1, A2, A3, and A4. So A4. So it will tell me that this is good. Why? Because I would start with X1, right? So if X1, so this is so let me be more accurate. So X1. So if the value of X1, let's say less than 10, so if X1 is less than 10, so I will divide my X1 for 2 parts. If X1 is less than 10, or it could be bigger than 10, right? So bigger than 10. So if X1 is less than 10 and X2, let's say this value for X2 is less than, maybe 20. So if X1 is less than 10, then I will look at X2. So if the value of X2 less than 20, so if it is less than 20, then I will classify these guys as, as the circle. So here, and if the value of X2 bigger than 20, then I will classify them as this rectangular. So which have good accuracy. And then, so I go through this split. So if X1 is bigger than 10, if I am in this area, then I will look at the value of X2. If X2 is less than, so here I will look at X2. So if X2 is less than 20, then I will classify as rectangle. Otherwise, I will classify as the circles. So this is the nature of decision tree. So in decision tree, we split it our area, our predictors area, x1 and x2, to some disjoint areas like A1, A2, A3, and A4, so that we can have a better classification accuracy. So the better classification accuracy means that I can classify all of the object, very accurately. So this is the nature of decision trees. Now, look, like this data is very easy, in fact, to partition. And in fact, how we can partition this, we can, examine different points, and then to see which one provide more, accurate results. And that's the algorithm is quite recursive. So we started, for example, by dividing this area for less than 9, and then we add maybe 1, 2, etc. And for x2 we do the same things. Then we see like which decision tree provided the most accurate result for us. But in some certain cases, dividing the area for like that, it becomes difficult like that. So if my data is like that, look, so let's say if I do have data in this form, I do have some data inside this triangle, and I do have some data like inside the other triangle. So let's say I do have some data here. So let's say these are some circles, and these are some triangles. So yeah, these are some triangles here. So all I want to do, so we have some predictor variables, x1, for example, first genes and second genes. So, and I want to predict, so what's going on to this guy, for example, here. So if someone has this x and y, so let's say this is 5 and this is 6. So I want to predict this guy. So what's going on to this guy, like here, or maybe in this area. So look, so this is part of my data, right? So it's quite obvious that we should in fact classify them as blue, not as the orange. So why? The support vector machine in fact is a way to deal with this kind of data, because both logistic regression, I mentioned that the logistic regression will draw a line like this, and based on that we cannot predict very accurately. So also the decision tree will not work here, because decision tree will divide this area for like this, and in fact this is not so much correct, because some of the observations will be misclassified. What support vector machine does, in fact, is that support vector machine can build us a hyperplan like this, like you are drawing a highway between two sides of the board. So this is a highway or hyperplan, or maybe an area between these two groups. So we want to build a very actually wide range, like wide hyperplan. So let's see like that. So this part, like this is one group, so G1, and this is G2. So we want to build a very large, very wide, the most widest hyperplan, the widest hyperplan, or the widest wall, or the widest row between two groups, so that none of the elements in this group can be switched with the other, or can be misclassified with the other. So this is the nature of support vector machine algorithms. So far we have learned two machine learning algorithms. One is called as decision trees, so which in fact is splitting the area of predictor variables, or X, for some disjoint areas, so that we can have correctly classified observations. Another one is called support vector machine, which, as I mentioned, we want to build the widest hyperplan between two groups of observation, or two class of observation, so that we can have the highest accuracy for prediction. So this is the nature of these two algorithms. Now, I am going to introduce the second algorithms that we developed, we are going to talk about. It's called as the random forest method, random forest, or RF. So essentially what the random forest, so we started with decision tree, right? So let me build you a tree. So a tree is like that. So we started from the root and we go to the leaf. So let's say this is the age, and we want to see if the guy will like some certain things or it develops some cancer, etc. For maybe less than 75 age, so it is non-cancer and then cancer, right? So this is a kind of decision tree. If I just I want to classify based on the age. And now the thing is that this age or this decision tree is based on one sample of observation. Now the question is, if I change the sample, is this I mean, how the accuracy will change if I change the data? So as it is known, decision trees like DT are in fact weak learner, in the sense that and sometimes they do like a little slightly better than just classifying by, by chance. For example, if you flip a coin and then if you classify people based on, the outcome of the coin, sometimes the decision tree are work like that, and it is not so much good. So that's why, in fact, a new method called random forest created to overcome this problem. So how the random forest works? So random forest, in fact, try to build many decision trees. So for example, I build another tree here, and I make a decision based on that tree here, and then I build another tree here, and then I will look at the tree, decisions, etc. So instead of having a tree, I will have a forest. Then, for example, I will look at the left-hand side. So here is non-cancerous, here is cancerous, and here is non-cancerous. So what I mostly see is mostly the left-hand side is non-cancerous, right? So then it is better than just looking by one tree. So I will look at the trees, and then what is the majority vote? I will apply that one for the classification. So, and the idea of random forest coming from, in fact, from an idea called, central limit theorem, central limit theorem, or another area, maybe let me tell you. So if X is an observation, a single observation, so this X will have a variance. So you know the variance in statistics, variability. So this X has a variability of V of X. So we can call this one as sigma, right? So now if I take a sample from this population, from this random variable with the distribution of F, if I take n sample from this, in fact, this population, if I take n sample, and if I take the average of those n, then my average will have a standard deviation or the variance of sigma squared divided by n. So what does it mean? It means that the average is better than, is better than single observation. So that's why, in fact, we created random forest. Because it will look at what's happening in the average, and the average is better for making a decision about anything. So that's the nature of random forest. So in random forest, so once again, so we are trying to build many trees, and then we look at the average decision, or what's the majority happens. So this is the nature of random forest. Another thing is called boosting. So boosting is another algorithm for increasing the accuracy in the decision trees. So how the boosting works? The boosting is, in fact, working in such a way that, so let's say we have like some data, so like this. So we have some data here in the XY region, so X1, X2 region. If I do have good classification in this area, so but not a good classification in this area, then in the next, so in the random forest, in fact, we do bootstrap sampling. So what does it mean? We generate sampling with replacement from my populations for many times, and then I will look at the decision, and that's the way that random forest works. But the thing is that if some part of the population in fact has much frequency than other part of the population, then I will have more accurate decision in this area, but not in this area. So the way that, in fact, we can overcome this problem is called boosting. So boosting is a method that in fact, try to take samples mostly from the area that the decision tree has weak performance, right? So decision tree may not have good performance whenever we have quite few observations in that area like this. So in boosting, we are trying to condition, or we are trying to mostly weight those observations or samples coming from those areas that decision tree has big, in fact, performance. So this is the way that, in fact, the boosting method works. Now, these four methods are quite common in machine learning. And in fact, in the practical situation, we don't know if my area or my observation is not like in XY coordinates, or is not, I don't have like one single variable or two or three variables. I do have maybe 25 variable or 20,000 genes. So which in fact depicting them like, or describing them in the dimension is quite, you know, cumbersome, and I cannot have any imagination for that. That's why many of those machine learning algorithms created to, in fact, to do the job. And what, in fact, we need to do in practical situation is that we need to examine many of those based on our data. So all of those machine learning staffs are data driven. We cannot, you know, prove that which one is better than the other unless we take we examine them in the, you know, in properly in the training and testing data. So now let me know if so far so good. Let me know, because if you have any question for this type, like for the basic of those machine learning techniques, I can help you from this point, so that you know, you can be like somehow you know, like familiar with the nature of these four machine learning methods, so called as decision trees. So the first one was decision trees like that. So this is a tree. The second one was random forest. So, and I mentioned that we created many trees like that, and then we look at the votes. So vote means that, okay, left, what happened mostly in the left hand side and what happened mostly in the right hand side. Then I mentioned for the boosting method, so boosting or in fact XG boosting. So in XG boosting, I said that, so in the random forest we have IID samples, bootstrapping samples, so which may not be good when in some specific areas we have quite few observations, and then the decision tree will have poor performance on those area. So boosting is a method to overcome that problem. So in fact, if we have two areas like this, so like I mean, so I do have an area that I have quite a lot of data here, and I do have like an area, I do have quite few area like data here. So in the boosting methods, I try to, in fact, to maximize the sampling from here, and then make a decision trees, and then make good decisions at the end. I mean, make good classification. And what else I discussed with you is that, so decision tree, so all of this DT, RF, and boosting, they are based on the partitioning the predictor space, or X1, X2 space. So let's say this is two variables, right? And based on them, we wanted to classify, will it be circle or will it be like rectangle? So this is my object. So I do have some rectangles, and I do have some, in fact, triangles. And now I want to in fact, to build machine learning methods that can tell to me if some observations for this X, what's going to be on here, right? Or what's going to be on here. So if I want to predict this guy, I mean, there is a new observation here, and I want to predict maybe at this point, I want to see what's happening here. Will it be circle or will it be triangular? So I mentioned that support vector machine is a nice method that can build a hyperplan, let's say like this, maybe. So for this area, maybe it can develop a hyperplan like this. So whenever something, you know, happens inside this hyperplan, then I will classify them as a circle. Otherwise, I will classify them as a triangular, right? So this is the way that support vector machine works. Now, we have two major things in support vector machine. One is called linear support vector machine, which can in fact we want to develop a linear hyperplan like that between two areas. So if my data are like this, so if I do have some data around here, and if I do have some data in this area, right? So let's say I do have some rectangular here. So in support vector machine, I try to build this hyperplan. I try to build this hyperplan so that it can classify my observation very properly. So this is called as linear hyperplan. But what happens if my observations are like that? So let me draw some pictures. So I do have like some observation in this form. So I do have a circle like that, and then I do have some other color or triangular like that. See? So now if I want to classify this observation, if I want to make any decision, so what's going on here? So here, what can be done is that it's called something called nonlinear support vector machine, in the sense that we can in fact create a like a circle like this, so that whenever something in between inside this circle, then we classify as a blue. And if it is this happen outside of the circle, then we classify as in fact this triangular. So this is called as nonlinear support vector machine, or I am simply called this one as nonlinear SVM. So because this, you see, this is a circle and this is not a line. So, and one also good things that let me tell you here. So we can also use in such situations something called, I mentioned to you, that KNN. So KNN also works for this kind of data, because I will look. So for example, if I want to predict some like what's going on in this observation, so let's see, this is x1 and this is x2. So for new x1 and x2, I want to classify this observation. So I will look at what mostly happens in this area. So what I see, based on one neighborhood, maybe this is 50-50, which is not good. But maybe if I look at maybe like two neighborhood, then I will see like mostly blues. So then I will classify the new observation based on x1 and x2 to go to the blues. So this is the way that again KNN works. Now, if that part is clear, so let me know, because I would like to answer your questions if you have anyone in this part. Any questions?
Okay, Dr. Reza, I will open the house to the audience. Anybody, if you have any question, please do unmute your mic and do present your question. Is there any question? Well, it seems that everything is clear, I suppose.
Dr. Naghmi, Assalamu alaikum.
Okay, yes, Dr. Kulsum, please.
I have a question. Dr. Reza, thank you for exploring the ideas in detail. I mean, it gives us a lot of clarity as far as the basic concepts relating to decision tree, hyperplan, RF, and boosting are concerned. My question to you is that you have mentioned that in boosting, when the decision trees don't perform better for the reason that there are a few observations that cannot, so the decision tree can't perform better. So we use the technique boosting. So my question is, Dr. that you have mentioned that we are going to weight those observations where the decision tree is unable to perform well. I mean, what is the process of weighing those observations? What would be the procedure, underlying procedure for that?
Yeah, there are certain, in fact, certain ways to do that. So if we want to be more, accurate, a very nice book written by Rob Tepshiriani and Hasti, they in fact, they give a lot of detail about that, but this is called as maybe weighted sampling. So we weight, those samples that the decision tree has not good performance. So we want mostly take the observations from those samples. So maybe we can use, maybe a stratified sampling or weighted sampling. That's the way that they do. So we want to take just mostly observations from that area or that part that decision tree doesn't work well.
Thank you, Doctor.
No problem. So
any other question? Okay, I suppose you can continue.
Okay, thank you. And so let me also give you two things why we say support vector machine. So because there are two vectors like this and this vector. So we want to find what is my support vector so that I can build the most in fact widest hyperplan between two groups of the observations. This is the name of, in fact, this is the way that we say support vectors machine. So we do have two vectors here, and yeah, that's the idea of support vector machine. And now let me, before going to the other part, let me mention to you something which in fact is very important, is something called variable selections. Sometimes our data is in fact we have quite a lot of variables, and mostly in gene expression analysis, we do have quite often a lot of variables, maybe 20,000 genes, which some of them are just noise. And now, if we want to do any of the machine learning algorithms like ANN, KNN, SVM, any of them, then they will work better in the training samples, because those machine learning techniques, they are called greedy methods, in the sense that, if this is like my observation, so like let's say I do have some observation like that, see, and I want to build a line. So I can go through and find like a line like this so that it can catch everything. But we, in fact, in the linear regression, we don't do that. So we will explain what the linear regression is, but I'm assuming that some of you might know that maybe we can fit a line like this, the best line, so that we can describe the data. So this is the way that, statistics working, and this is the way that machine learning working. So in machine learning methods, we have a lot of parameters. We can set a lot of parameters so that we can catch the data or catch the pattern in the training sample, but we cannot do in the testing sample very well. So that's why we need to be very careful when we want to draw any machine learning algorithm. So one good thing is to, in fact, to removing the noise. So what does I mean by the noise? So let's say if I do have quite a lot of variables, let's say I do have like x1, one variable, second variable, let's say I do have x 20,000, right? So 20K. So instead of, working with 20,000 variable, so hopefully, one day there will be maybe a session so that we can only describe how we can do variable selection. And in fact, we are trying to find, to spare a time to do the variable selection as well. So what is here is, I want to emphasize something why machine learning created while we had statistics. So the main advantage of machine learning is that the first advantage is they are free of assumptions. So all these machine learning techniques, they are free of assumptions, right? So we don't need to have linearity assumption, normality assumption. So they are free of assumption. The second thing is that so sometimes they are better, in the sense that they, you can have outlier as well. So if we have outlier in the statistical part, sometimes we need to remove the outliers. But mostly machine learning, because they are learning from the experience, they are free of, like this assumption. Sometimes, we cannot say it is good. I mean, sometimes they really, suffer from the outlier as well, but mostly they are okay with that. But the most important thing is being free of any, statistical assumptions. So, which is in fact good. However, even with the machine learning algorithms, if we have quite a lot of variable, like x1, x2 until x20K, if I do have 20,000 variable, let's say if I do have only like 200 observations. So this is called as, Dr. Saleha was asking me in the first, in fact, in the first ML workshop, what is the high dimensional and what is the big data analysis. So if the number of predictors or variable p bigger than n, so I do have 20,000 k and I do have 20 cases. So sorry, 200 cases. So this case in here, I do have quite a lot of variable than the observations. So in this way, the traditional statistical methods like linear model will not work, because the whole MSE in the regression analysis will have something, you know, called the MSE divided by SSE. So I don't want to go through that. So then one of the assumption for that, for the regression analysis or for the multivariate regression analysis was that, so we must have, in fact, more observations than predictors. So for example, if I do have 20 predictors, then I must have at least 100 observations so that I can build a regression analysis or regression model. But in fact, in the real world, we see, oh, I do have 20k predictors, only 200 cases of people. So here, the traditional statistical model like the regression model will not work. And I mentioned last time that we use something called, in fact, variable selection or lasso method, lasso. So lasso, in fact, is like a non-parametric method. It can do variable selection, V-selection or feature selection. And whenever it do feature selection, then I can reduce the number of predictors from 200k. Maybe I can be like, I can find a small number like 20, so that with this 20 variable, I can have most of the variability in this data. So which in fact, we will explore this in the one of our session, maybe the principal component analysis, etc. So what I am trying to say to you is that simply we cannot, I am going to run the algorithms, and before that I am going to tell you that if I do have quite a lot of variable, and if we want to build a machine learning models, then it will not have a good performance unless we can remove the noise. And how we can remove the noise? One is to use the lasso method, so that we can only, you know, keep a few of the variables. So in the sense that they can have, like, they can capture the essence of data. I mean, they can have most of the variability in the data. So okay, now I think, so if you have any question from this part of the variable selection, or how we can deal with the case that, you know, if we have, this is called as something we say that high dimensional data analysis. So we have high dimension, I mean, we have P more than N. So this is called high dimensional data analysis, which is something that we are working in Tabriz on that. So if you have any question like in this area, I would be more happy to provide answer if I know the answer. So please do ask, and if you don't have, then I am going to the codes. So to run the codes and see you and show you how we can do the codes. Any question?
I think, Dr. Reza, maybe you can continue with the code, and I can also ask people to jot down their questions. Maybe we can have the questions put together later also. Will that be fine, Dr. Reza, or do you want the questions right now?
I mean, for this part, just I want to be clear for this part. Everything is okay for this part. Then we go through the question. I mean, so if it is clear, I can go directly to the code. So since there is no question in this part, so I'm going to the code. So in coding part, yes, go ahead.
I'm raising my hand. No, you can see for now.
Yes, please go ahead. Yes.
Yeah, thank you very much for the clear presentation. It's really wonderful. The way I understand the boosting is that you take any method and then you can boost it, and then the boosted method will always outperform the original method. If this is true, and if this is true, I don't really see why. Is it always the boosted method better than the original method? That's one. Go ahead.
Yeah, let me explain you. So if our data is in fact is in such a way that you know, we can provide it very high accuracy by a simple method like decision tree, then we like this decision tree. Mostly, in fact, medical science, or for those people who don't have quite often a lot of knowledge in the machine learning, they like decision tree. Why? Because the decision trees are quite simple and quite straightforward and quite useful. But if we don't have good performance in the decision trees, we expect that we can improve them by boosting methods. So our expectation is that, I mentioned, like, there is no theoretical, in fact, explanation for that. However, based on simple statistics, since we know that the average of the population the average of the sample will always have less standard deviation than the single observation. We expect that in this sense, decision tree will have, the boosting methods or random forest methods will have better performance than the decision tree. However, there might be some cases or situations that, you know, our data cannot, in fact, you know, clarify, cannot predict the outcomes, you know. For example, for cancer, still like the AUC is 65%. We explored a lot of genes, 20,000 genes, but at the end we come up with the AUC of 60% or 67%. What we can do? We tried the best. We tried decision trees. So slightly we improved the decision tree by boosting, but we cannot go further because our knowledge is still, you know, incomplete regarding to the genes or samples. I mean, we expect, but sometimes, you know, it just simply could not improve, you know, quite significantly.
Any other question? Any question by anybody?
You have one more?
Excuse me. I have a question.
Yes, please.
Doctor, kindly tell me, if we have an outliers in response variable or outcome variable, then what will be the effect on lasso? Whether lasso, as you told that it is non-parametric, so if we have outlier in response variable, lasso results will be affected or not?
Yeah, so let's discuss the response is categorical or in fact continuous. So if the response is categorical, let's say we have like a 3 category. So 2 category have 55 observation, 1 category has only 2 observations. So here, in fact, the third category is not so much important for us. And it seems it is like an outlier, something unusual, right? So in this case, we should remove those 2 observations to avoid the problem. So this is the way that we can do, and definitely the lasso will be affected in this way. Now, if we go through the continuous outcome, we might have such observations in the outcome variable. So again, in this case, you know, the lasso is like penalizing the loss function, you know, is constrained to some conditions. So since the error will increase by having those, in fact, by having those non-usual observation, then the error will increase. However, we are trying to minimize you know, to subject to some constraint. So the best way to me is if there is, so there are 2 kinds of outlier, right? One is called as they are real outlier, or maybe they are just some data are, you know, reported missing. So we need to check them. So if they are really data, not the error, then sometimes keeping them is better because they are real, they are truth. For example, we have some people with prostate antigen, with higher prostate antigen. And in fact, we developed a paper in statistics in medicine for that sake. So before us, they used the normal regression model. So they removed the outlier. I mean the higher prostate antigen or PSA. So, but in fact, we are trying to work on that. We are trying to work with unusual, in fact, observations. Or in my case of a study, for example, for preterm birth. So less than 5% of the people will have preterm birth. I mean, gestational age less than, you know, like 37 weeks. So if I consider them as an outlier, then, you know, it will not make sense. So in this case, I mean, categorization will work. So that, I mean, instead of using continuous measurement, we should categorize them and use logistic regression. That's the way that, in fact, can be applied when we have a quite few observations that maybe seems to be an outlier, but really they are not outlier. So, and let me explain here, when we have, in this case, so we have a rare events like preterm or like cancer. One group has, you know, only 1% of the observation, another group has 99% of the observation, or in the fraud detection. So the rate of fraud is, we expect to be quite few, maybe 1 out of 1,000. So if I do have 1,000 sample, I have only one, in fact, fraud. So if I go to 10,000, I will have 10. So now if I use any of those machine learning algorithms, then we may come up with something called imbalanced classes. So we need to balance the class and then work through the machine learning algorithm. I have prepared some parts the next session to show you how we can do, in fact, the machine learning method with the imbalanced data set. Okay, so any other question?
Thank you very much for that. I think, Dr. Reza, we should continue with the demonstration of the code now, because we can have more questions maybe later. Yes.
Sure. So I provided the code. In fact, good news is that the coding part is quite simple for the machine learning part, for this machine learning part. All we need to do, so I provided a binary category variable and also a multinomial category. So let me run the code and run the data. So I have some, I need to, in fact, in order to use machine learning, I need to have some library. So yeah, let me go first with the binary, which is the simpler one. So I need some packages. So some of those packages are not needed. For example, Amila or mice. So these two packages are for missing observation, which in fact I don't have here. Mostly what is most important package for me is caret package. So the last one. So the caret package here can perform the machine learning methods very well for me. And also I mentioned to imbalanced class in the next session, I will tell you, is called random oversampling technique. So in the library ROSE. So I'm just running the whole things. So, and then, so I am using the iris data. So the iris data, which is a known data set. So let's see the first few observations of this data. So let me bring the first 6 row of the observation. So what we see here, we have 4 continuous measurement: sepal length, sepal width, petal length, petal width, and the species. So we have 3 kinds of species: setosa, versicolor, and virginica. So in fact, since I am, you know, the reason why I want to give you know, binary category and multinomial category, because in binary category, I will need to evaluate the prediction accuracy with some different things than when we have multinomial category. So I changed my data to, in fact, to binary. So first things that I want to do is I need to have a training data set. So for training data set, I need to create the training index by using this function, create data partition. So I use 70% of the data for training and 30% of the data for testing. Now the question is why we use 70%. So there are some studies, in fact, has been conducted to see which part, you know, which separation is good: 70%, 60%, 50%. But mostly they come up with the conclusion that 70% is better. So first, for any machine learning algorithm, see, so far I haven't said any machine learning algorithms. For any of them, I just need, in fact, to divided my data for 2 parts. One part is training, so which in fact I can do by this function. So I can see the indexes here, and then I can use so I can provide the indexes. Then I can use I can find the training data. I see the dimension of training data. I do have 105 for training with 5 variables. So, and I can see the class of those observations. So I have like numeric observation and also a factor for the outcome variable. And I am going to, so the job is prediction of the outcome variable. So my outcome variable or my response variable or my Y is species. And my X or my predictor or my explanatory variables are the characteristics of the species. Is sepal length, sepal width, petal length, and petal width. So I want to give these characteristics, and for the for new observation, and I want to see what's the outcome, or what will be the color of this species. So I do have the levels. So for the training, for the outcome variable, I do have no and yes. So in any study, if you want to have binary category, so if in cancer study it will be cancerous, non-cancerous. If somebody going to or it could be buy and sell, it could be success, failure. So this is a binary outcome. So here is my testing index or my testing data. Now I can look at the proportion of my data, the frequency. So I do have 66% of no and 33% of the yes. I can have a summary of my training data. So and now I can split, I can say like my X of training of X, and so my Y is the training data, the fifth column of training data is my Y. So, and let's do a box plot. So we did the box plot last session here. So here is my box plot. It can show me how the distribution of those 4 variables. And then I can go to to find the feature plot. And so these plots are just some graphical plots that shows the distribution of those 4 variables for no and yes. So these are the distribution of these 4 variables for no and yes category. So now we can scale our data set. So we do scale for some specific reason so that we can compare them. So this is a feature plot, and this is something that we can understand from here, that our classes, so we have 2 classes of observation. One is this line, this color pink, and this is blue. So I see the overlap here, right? And I see how difficult the job of classification, because there are quite a lot of overlapping in this observation. And the nice things we are going to explore is that mostly those techniques will correctly classify these 2 classes of observations. I mean the blue and the pink. So yeah, and we see it's really by looking at the distribution, we cannot have a good classification. So what else I can need in any of the machine learning, in fact, is I mentioned to you that, so first we need to have training data set, and then I need to build my machine learning by something called cross validation. Why? Because I will have some hyperparameters, which in fact those are quite important, how we can obtain those hyperparameters. So we can use them we can use this function, train control function, to set a 10 for cross validation for the training data. This is training data. So I set 10 for cross validation. So for binary category, I will use metric or in fact, the optimization. I will do optimization subject to ROC curve, not the accuracy. If I put the accuracy, it will not be good when I do have imbalanced data set. So here the data was not balanced, but it was 30-70, wasn't so bad. But if I have 1%, 91%, sorry, if I have one class of 1%, another class is 99% of the observation, then putting the metric as accuracy will not be good. So for binary classification, that's why I put ROC, means the receiver operating characteristics. So that is my metric or my measurement to check the accuracy of the result. So I set the term for cross validation here by using train control function in the current package. Now, I'm fitting my models from scratch. So in the last session, we tried to use, logistic regression. Logistic regression can be done by, so yeah. So let me explain this function. This is the most important function in fact, in current package. The function name called train. So train will include several models, several machine learning models. This package is in fact awesome because we can build any of our machine learning models based on, this just simply by this train function. So I do have a name for this function called fitGLM. So I will use train function. My outcome was species, and then I will use all three variables. So whenever we do maybe next session, we will tell that we will not have all like tilde dot, because if I do have 25,000 variable, it will provide me a lot of, in fact, working, because those machine learning algorithms even may not converge if I put all of the predictor variables in the model. So here, but for now, since we have only 4 variables, that's okay to go this way. So yeah, so this is my outcome variable. It can be affected by the all of the predictors. So I put my data name. So look, my data is training data. So I build my models in the training data, and then my model is GLM. And my metric is like metric that I had, ROC, and I use the train control function to, in fact, to do cross validation. So that's quite easy. And also I use the GLM met function. So I tried them list. So since this is run quickly, I don't have worry about the time. So we fit quadratic discrimination analysis, linear discriminative analysis. So what we see is the code are quite simple. So we just need to change the method name. For example, we do have QDA, we do have LDA, and we do have KNN. So we just simply need to run them, right? And the code is available. So for any other data set, we just need to change the outcome variable here and the X's here. So, and now I fit the decision trees. So the decision tree, we also use the same function of terrain. So my outcome and so species, tilde dot, all of the predictors, comma, my data was training data. I am using the rpart function in the terrain, and I use the metric and train control. Let's see how it looks like, the decision tree. So if I do have like the decision tree plots, see the plots are coming, but let me have this fancy plot for you. So let me zoom the plot. So what we see is, yeah, this is a really decision tree, but kind of, the picture is not so much clear. Maybe it's dark, but so what we see is we have no of 60% and 33%. So so this is my decision tree classification algorithm for this data. So the decision tree will look firstly at the petal length. If the petal length is less than 2.5, then we classify them as no. So the accuracy is 100%, which is so much good, right? So we, based on petal length, we correctly identified 100% of the data, so which is good. And then if the petal length is more than 2.5, then I will look at this variable. I will look at the petal length. So if the petal length is more than 4.9, then I will look at this part. If that is yes, I check this is so if that is more than 4.9, then I will classify as yes. So the classification accuracy for this part is 97%. And if no, if the petal length is less than 4.9, then I will classify them as no, which in fact the classification accuracy is 92% in this case. So this is the way that decision tree can work for us. So I think now it's the time to.
Yeah, yes, Dr. Reza, I just wanted to say that this is the time for a short break. So if it is okay for you, then we can have a short break here right now.
Yeah, thank you. Yeah, that's good.
Okay, all right. Ladies and gentlemen, we'll have a short break of 5 to 7 minutes. Thank you. Assalamu alaikum again. We are going to begin the second part of the workshop and the program. So Dr. Reza, are you going to continue or is it going to be Dr. Alireza?
Assalamu alaikum. So thank you very much, Dr. Saleha. I'm continuing a little bit, then I will leave the session to Alireza.
Okay.
So Alireza will in fact tell us mostly about linear regression. So I'm going to cover those machine learning techniques that I told about them. Then Alireza will talk about the linear regression model.
Okay, then please go ahead. Thank you.
Yes, thank you very much. So I'm sharing my screen again. So yeah, we talked about the decision trees. So sorry, do you have my screen, Dr. Saleha?
Yes, yes. Yes, I had it, but now I don't have it. I think you have to do it again.
Okay, sure. Okay, yeah. So we described the decision trees and how it nice. So one of the good things about the decision tree, in fact, is the picture of the decision tree. Or really, we can use it very simply. And mostly clinicians like to have decision tree instead of boosting or random forest, because we cannot have put a picture for those techniques. Though we can have better performance. But whenever the performance is quite similar, we should use decision tree because it's quite simple and it can provide us the picture. So now this is another way of providing the decision tree by this function, R part plot. So we can provide separate, like the function. Not so here I do have all three decision tree. They all are the same, but the shape of the figures may be different. So now, so let's go to the random forest. So here again, to the random forest model, we don't need to do anything except changing the method to RF in the train function. So I do have like the same thing for decision tree, for GLM, for other methods, but I just need to change the name is to be random forest model. So I can have the random forest model. So like random forest, yeah, it has been run. Now I can see my output for the random forest. So what I see here is that this shows the how the sample. So I had 4 predictors, 2 class variables, no and yes, and we haven't done any pre-processing. For this data, I have used 10 for class validations. These are my sample size, 95, 94, 94, etc. And these are my my results. So we have a hyperparameter. If you remember, we had something called hyperparameter. So hyperparameter for random forest is the name is mtry. So mtry can be 2, 3, and 4. So now I will look at the result of rock sensitivity and the specificity to see which one is provided the highest ROC. So what we see is that for 2, we have ROC of 99, sensitivity is 97, 91, but mostly they are quite close. But the final model, by looking at all of the digits, it seems that mtry equal to 2 is better model. But for this data, in fact, they are quite better, both like 2, 3, I mean, all of 2, 3, 4, they are good. But if we go through the other digits, we may choose mtry equal to 2. And in fact, we don't need to do that because Caret, smartly like will choose mtry equal to 2 for the prediction part. So then we told about like boosting. So this is the function name for boosting. We just need to have XGB3. So means the gradient boosting decision trees. So we can run this model as well here. So everything is like same. So one thing that, so let me go to the decision tree part and show the result of decision tree. So in the decision tree, we have something called complexity parameters. So, and again, since I put my metric as ROC, it will provide me the ROC. Now we see, for example, for the complexity parameter of 44, I do have quite few AUC, ROC is 64%, which seems that this complexity parameter is not helpful at all. So it shows that the best CP was 22 for this decision tree, and in fact this function will choose to 0.22 for my prediction. So we run XGBoost and we see the result of this function as well. Oh, sorry. So we run the XGBoosting. So they are, so if we have like a large scale data set, then these algorithms kind of, slow because they are repeating the sampling and they are repeating the performance, etc. So see, they are, so I have only 100 observations and only few variables, it will take some time. And this is one of the complexity of these models. So hopefully this can be done. So after that, I will run the support vector machine. And by that, we will have some pictures and figures, and then we compare those algorithms. So let's see, hopefully this algorithm can be run shortly. Yeah, this is the issue with the random forest. Oh yeah, it's done. So we can look at the results of this method. So we see, what we see is there are quite a lot of hyperparameters here, right? So, there is no free lunch in statistics. So that's the truth of the world, because when we add more hyperparameters, then we come to model complexity, maybe, some computational, in fact, expense, etc. But this one has been done. So we see the best parameter. So the final model were chosen in round 50, max steps 2, ETA 4, gamma 0, and the other parameters here. So we see there are many parameters for this model, right? So the package can, smartly choose most of them. I mean, all of them wisely. And now we go to the support vector machine with linear support vector machine. Again, we use the same function. So we just need to change the method to be SVM linear. So we run the support vector machine algorithm as well. And what we see is this is quite, like simply run. So, and we see the results, the final results of this model. So, and let's see like what is the result for the nonlinear support vector machine. So as I mentioned, really in the data set, we cannot see which one worked better. We need just try and then test in the testing data, evaluate in the testing data to see which one works better. So this is my support nonlinear SVM. And let's look at the result of nonlinear SVM. Now, I am going to compare all of those results by resampling to see what's the results for all of those techniques that we used in the first session and the last session. So here is the AUC. So, and we see the beauty of the machine learning techniques here. So what we see, for example, in support in nonlinear SVM, the minimum AUC was 96%, while in logistic regression, it was 53%. So which is good. So if we go to the mean, we see that the logistic regression had the poorest AUC. You see, this is for logistic regression. If we examine based on mean or even median or even any of those, logistic regression had the worst in fact performance. So, and what we see is the other machine learning methods, they work very well, very better than the logistic regression. So we don't want to criticize the statistics now, because it's too soon to say that logistic regression had worst results, because these are based on the training samples. And I mentioned to you that in the training samples, we expect that the machine learning methods will have better performance. And this is very, very critical when we work with the healthcare data. It is so much dangerous to report these results, because in the testing, they will not have such a great performance. So now let's go to the dot plot. And this is the
Dr. Reza, I have a question. All these which are showing 1.000, etc. So these, I mean, that is the best possible, right?
Right.
The number one would stand for the best possible. You could not be better than that.
Yeah, for logistic regression, I cannot be better than that. For the elastic net, I cannot be better than that. See, so yeah, so these are the best performance that I got in the training data set based on this measure of accuracy and based on this cross validation method. So what we see is that so let me in fact magnify this picture. So what we see is that in the training data, KNN, SVM, random forest, QDA, XG boosting, they all were better than the logistic regression. So, and one reason is that we didn't say here is that logistic regression will have poor performance if we have multi-collinearity between the variables. So some of my variables here was so much correlated. So if I draw you the correlation of the predictor variables, you will see some of them was correlated. So when I have correlated variables, I shouldn't use like logistic regression. I should go to use elastic net. So which in fact we did here, elastic net. We used elastic net. But even using elastic net, it improved the logistic regression from the worst case to be like to increase the performance to come like here, but it's not enough. So it means that here there is something called nonlinear relation. So in fact, the one advantage of the machine learning method is, in fact, is that they can work with nonlinear relations. The whole logistic regression, linear regression, they all have something called linear. So which in fact, maybe that is not true. If we have quite a lot of data, if we have nonlinear pattern. That's why what we see here is that KNN and SVM have better results, because this is a nonlinear SVM. And I mentioned to you a picture of nonlinear SVM. So these two had better performance because in fact, the structure of my data was nonlinear, not the linear. If you remember, we had some, bimodal, we had some, the distribution of X was different. So it shows that here machine learning really worked in the training data. So let's wait to see what they can do in the testing data as well. So I can use like the testing data. I can use quadratic discrimination analysis. I can use confusion matrix. So for example, for QDA, and I see a sensitivity of 100%, specificity of 86%. And let's say I can use like GL. So I can use also the RAC. I can provide the ROC, etc. And so let me bring one of my machine learning models. So fit support vector machine here, the nonlinear, to see what's the performance of so let me go through the random forest, RF, and let's see if it has the same performance as in the training data. So this is RF, the performance in the training data. So, okay, this is. Yeah, what we see is that, so let me do it, this is as RF. So what we had, random forest has very good accuracy in the training data, but when we go through the testing data, so the AUC was 100% in the training data, but when we come to the testing, the AUC decreased 5%. So, and we see also the misclassification of the random forest. So we have two misclassification for the random forest. So in the same way, we can, in fact, we can explore in the testing data to see which of those techniques provided better AUC or accuracy to me in any given data set, and then say that that method works better than other methods in the testing data. So this picture here is quite misleading, because in training, we will have better performance for those machine learning algorithms, but we may not have better performance in the testing, in fact, samples. So this is the univariate category. I did the same thing for the multinomial category. I'm just running the whole things at once. So in multinomial category, instead of having one categories, I do have 3 categories. So let me run this code again. So yeah, so here is my outcome variable. So I do have three categories: Setosa, versicolor, and virginica. So, and then I do the same thing for training and testing, feature plot, etc. So, and now I put here, yeah, here I also see, let's look at this picture. So let me magnify this picture. It doesn't. So yeah, so what we see here, we see the 3 class of distribution. So this is the distribution of the blue. This is for the green, and this is the distribution of the pink in the petal lengths. And what we see here, that especially for this variable and this variable, there is overlap. So for this variable, we can, in fact, we can classify based on, you know, these values, petal length. If petal length is less than 2, maybe we can classify these observations for blue. But here there are some in fact, overlaps, which makes our job is difficult, really difficult. That's why we use machine learning to prediction. So we can use now the same way we can use the statistical method of multinomial logistic regression. I use the same function. Here we need in fact, to check something. When we have multinomial category, I will use accuracy, I will not use AUC, I will use accuracy. And again, I will use a method equal to cross-validation to find the optimal hyperparameters. And mostly the number of cross-validation between 5 to 10 is enough, is okay. So, but I'm mostly, I will trust more to n equal to 10, because it will provide better, you know, higher information or better information. So I am using like the same way as a multinomial logistic regression, linear discriminative analysis, KNN, and here is my decision trees, and we see how the decision tree looks like. And now I am using this the fancy plot. So this is a quite nice plot. Let me see if I can magnify this plot for you. Yeah, we see so how the decision tree is. So so we have outcome variable so of balance class of 33%, 33%, and 33%. So in order to classify, I will look at the petal lengths. So if the petal length is less than 2.5, then I will classify that my observation as Setosa, which in fact very good, because the prediction accuracy is 100% here, which is very good, right? So, and it's enough to look at, so in order to predicting, you know, like it's enough to have only to look at the petal length of less than 2.5. This is very good classification. If petal length is bigger than 2.5, then I will look at the petal length. And then I will check whether or not it is less than 4.8. So if it is less than 4.8, then I will classify as versicolor. Otherwise, I will classify as virginica. And I will see what's the classification accuracy. So here I do have 94% accuracy. Here I do have 97% accuracy. So, and this, the last digit is 34%, shows that how much of data are classified for virginica, how much classified for versicolor, and how much classified for the setosa. So,
Dr. Reza, what is the minimum, like 95, 4%, 97? What is the minimum by which you would be satisfied that whatever you have done is okay?
Yeah, no, we said that the more close to one is the better. 3 can do for this data, you know. So we don't have like such a cutoff point, but we want to have in a way that, you know, mostly, let's say this is 30%, 30%, then you know, 60%. So we must to classify the majority, not like equal. So if it comes to equal, then it's paying. We yeah, that's the
okay, thank you, Dr. Reza. I do.
So just we had like a multinomial category here. So
Yes.
I have a short time. I have to make a brief about the regression models and try only to make an introduction about the regression and give that to leave that in details for next session. As we know, linear regression is used to predict the value of an outcome variable y, for example y, based on one or more input variable or variables, namely x. The aim is to establish a linear relationship or, for example, mathematical formula between the predictor variables and the response variables, so that we can use the formula to estimate the value of the y when only the predictor or predictors x values are known. For introduction, the aim of linear regression is to model a continuous variable y as a mathematical function of one or more x variable, so that we can use this regression model to predict y when only the x is known. The mathematical equation can be generalized as follows. You can see it here. In this mathematical formula for defining the relationship between the y's and x that can be explained about the mathematical relationship between the xi and y. Epsilon I is a random error term that usually is unknown, and it's the error term that the part of y the regression model is unable to explain the variation of x, variation of y by x. So in this equation, we try to find the beta 0 and beta 1 that they can explain this relationship as much as better okay, use okay, in this plot you can see the all of the introduction about the variables and parameters that we should know about them in the regression models. You know the slope of the model is a coefficient relationship between x and y, and beta p0 is intercept of the model, and epsilon I that can be estimated by EIs that EI is that yi minus yi hat. That yi hat is the estimated by the regression model. In the simple linear regression, we have only one predictor x1 and the two parameter beta 0 and beta 1. But if we want to use a regression model and explain the y, it's our response variable by some other independent variables, we should make a relationship between these variables with the y. That it will convert to multiple linear regression, and so we have much more coefficients that we should estimate them. Finally, we have observed data that you see here as a y, and predicted data that is obtained by the data, and our error will be epsilon, that is y minus y prime. In the multivariate regression, if you want to make a relationship, our linear regression will convert to hyperplan that can obtain by minimizing the errors. Linear regression or other regressions are very different types of the regression models. From the first of our sessions in this workshop, we tried to find best decision classifications to classify our response variable that it was categorical. And in the regression, we try to find a relationship, the y that is continuous variable, and we have to make a relationship to the explanatory variables. I briefed very important and very well-known the regressions that we will try to cover them in the next sessions. For example, polynomial regression, support vector regressions, and the decision tree regression, random forest regression, and reach and lasso regression. And the last time is that the logistic regression that we talked about that the previous session. Okay, I don't try to talk about the details of the regression models because it gets much more times. So we don't enough time this session. I try to make a code about the simple linear regression to how that it is work in the R. For example, I try to use the very similar data that you can find that in the special RStudio software, that it is named CAR. the car is that the cars is that data that we have two variables. The response variable, the response variable is that this we say that this that is a distance of the cars, and speed is the speed of the cars that we want to make a prediction distance by this set of cars. Then we have two variables, speed and this. Time of data is that we have two variables and 50 observations, and its plot. You can see that here. You can see a little. It's near to linear relationship between these variables. Okay, in the R, we can use this order to make a simple regression model that it is LM, and our response variable is cars $this, and the covariate matrix covariate variable is that speed. If you run it, we see that in summary of the model, you can see the model is that here, and the residuals summary is here, and the coefficients that we estimated by this model is that the intercept is minus 17 and 17.5, and the beta 1 hat is that 3.9, and others for the and other points about the these coefficients. You can see the standard error is that these and the t values for testing the these coefficients. That if we want to see that if these coefficients are significant or not, we use the t test, and we can see the p values. You can see the p values are more than 0.01. In the 0.05, you can accept these coefficients. But if you use 0.01, you cannot accept them, because accept the intercept, because its p-value is greater than 0.01. But here we use 0.05. At the last of the summary, you can see the RSE and the R squared. That R squared is best the best variable that we can use that to see how much the model can explain the y by x. So here, if you see that the 6.65% of the variation of y can explain by the model, and some of them means that 35% of the variation cannot be explained by this model. The last statistics is that F statistics that we can use that to know about the significantly about the model, and you see that its p-value is less than 0.01 and 0.5. The model is significant. In the next, you see the model regression, linear regression model. You can see here how it is fits on the data, and the next plot you can You can test the residuals if they are normal fitted or not normal, and they are independent or not. So here you can see the residual versus fitted values. You can see we don't see a very significant model in the residuals. The residuals can be realized independent. And about the normality, you can see the QQ plot. Some of the values of the residual are out of the QQ plot. Then we have, then maybe we have some outliers, and we should fix it. And other values, other plots, for example, scale location plot, and residual versus leverage values. Leverage values that the converted value of the x, that we can use them to see how much and how many value of the x are outliers or not. I will try and explain about much more about this model in the next session. I don't want to. I don't like to get much more time. So thank you very much to this time and this.
Thank you, Dr. Alireza. That was very good. And you know, I was particularly interested in that graph where, I mean, that diagram where you were showing all the different kinds of regression that can be. And certainly we should be reviewing and learning about all those different types of regression also. So yeah, that's the one, that's the one. Thank you very much. Okay, thanks. So now you can
cover all of these algorithms in next sessions.
Right, thank you. So you can unshare the screen, and then I will share my screen.
Okay, okay. Thank you very much.
Thanks. All right, I will now share my screen. So as you can see, I was taking all these screenshots, and now I can get to my slides. So many thanks to Dr. Reza and to Dr. Alireza. You know, what we are getting in 2 hours time, I know that you've been spending days upon days and weeks on preparing for all this for us. So that is very much appreciated. And now, ladies and gentlemen, the next thing is the keynote address by Associate Professor Aisha Bilgin. And I had requested Dr. Sharka, my dear colleague, to present her resume to all of you. But Dr. Sharka has informed me that for the past many hours, there is no electricity at her house, and also she's not having the Wi-Fi or the mobile data at this point. So unfortunately, she was unable to attend today's program. So I will have now the honor to invite the president-elect of the International Association for Statistical Education to present to you her keynote address. But before I do that, I will have the honor of presenting to you a short summary of her academic and professional achievements. So, ladies and gentlemen, Associate Professor Aisha Bilgin is active in the statistical analysis and design of studies in health and statistics education. Her research in health developed to include adolescent health and recently studies related to breast cancer, multiple sclerosis, and Alzheimer's disease. She is one of the pioneers on applying machine learning to health data sets. Recently, she was awarded Excellence in Research 5 Future Shaping Priorities for Healthy People. And this award was given to her by Macquarie University, where she's associate professor. Aisha has won several learning and teaching awards for her outstanding contributions to student learning as ALTC citation for outstanding contributions to student learning. I think, Aisha, one day we must have a talk coming from you to tell us more about this one so that we can apply some of this in our teaching and our work. Aisha's pedagogical research interests are focused on statistics education, such as learning approaches in statistics, impact of learning spaces to students' learning, and the like. As I have already said, she's president-elect of the International Association for Statistical Education, IASE, of which I also have the honor of being a life member and was also given the honor of being vice president for 1 year. The title of our talk today is Machine Learning Application for Health Problems. Prior to inviting Aisha to start her keynote address, ladies and gentlemen, I want you to know that at this moment in time, actually for the past hour, 2 hours, we are having with us Professor Joachim Engel, who is the current president of the IASE. We are also having Teresita from Argentina, who has won an award just, I think, yesterday, and that I saw on the Facebook, and congratulations to you, Teresita. We also have with us, as I have said earlier, Professor Ali Hadi from the American University in Cairo. And there's so many other people. And I would like to say that after the closing of the workshop, I've requested my colleague, Dr. Wasim, to not stop this session, but to let it go on. And I would like to have a conversation with all of you. And all the participants are welcome to stay on if you would like the informal conversation. So thank you very much. And now I think, Aisha, you would like to share your own screen, I think. So if that is the case, I will stop sharing mine. Is this correct? You would like to share your own screen, is that right? I think I can
sorry,
stop.
I was still unmuted, so I just stopped.
Okay. So I will stop sharing mine now. I think I should do that quickly. And I will now let you share yours. Thank you so much.
I think you can see my screen now. Is that right?
Yes.
That's good. Okay. Saleha asked me, I think 2 weeks ago, whether I could do that. And it took me a while to reply to her email because we are at the end of our session here in Australia, and I was busy with all the marking and everything. But I said, yes, I'll do it. And I only prepared my presentation last Friday, but I've been thinking about what I can give you in that presentation. I specifically wanted to join you from the beginning so I could see what you're talking about. Hopefully my talk will relate to what you have been talking about a little bit. Let me just see how I can move here. Okay. So, I mean, I'm just going to take you one little step back. I know that both Reza and Alireza talked about it, but how I see machine learning is simply having the raw data and converting it to information. This should give you some indication what we're trying to do. I mean, if you think about that, this is not just machine learning, but also statistics. We take the raw data, we model it, and we turn it into information. Without the raw data, we can't do it. But in statistics, what we also pay attention a lot is how the raw data is pre-processed. I'm not saying that it's not done in machine learning, but when the data is really large, it might be a little bit tricky. And I'll talk about that at the end as well. So these are some of the things that I usually share with my students when I'm teaching some of the techniques. And here, I'm mainly using a couple of softwares. I mean, the one at the bottom right, the one at the bottom right is SAS Enterprise Miner. This one I'm using here is IBM SPSS Modeler, and some of these results are also coming from IBM SPSS Modeler, and this is coming from R, and similar to what Reza was talking about, decision trees. And as you can see, neural networks, decision trees, naive-Bayes classifier, logistic regression, and there's many more techniques in machine learning, and every day they keep changing, and it's possible to do it in not just with one software, but many different softwares. And you can see here also, I mean, market basket analysis, maybe you've already talked about it in an earlier session. It's one of the undirected knowledge discovery tools, but it can also be used as a supervised learning tool. So directed knowledge discovery in a sense. I'm just, again, taking you one step back. We are all coming from stats departments, as far as I can see. And what is statistics to start with? I like this definition a lot. Statistics is the science of learning from data or converting data into information. So that's what machine learning is doing as well. I mean, there are many other descriptions of statistics, what it is. And the one that I don't like very much is, it's called that statistics is a sub-branch of mathematics. I don't like this definition one little bit because I don't agree with it. We are using mathematics for sure, but in my slides, I'm also using English. So does that mean statistic is a sub-branch of English? I don't think so. No one is claiming that, but with mathematics, they are claiming that. The reason I don't take this, because if you go back to history and look at how statistics developed, it's not developed as a part of mathematical tools, but it's developed as tools using mathematics to solve the problems in agriculture, in health sciences, in engineering, and so on and so forth. So statistics is the science of learning from data or converting data into information. That's basically what machine learning, data mining, and all these kind of new buzzwords are doing as well. But there is a big difference. I'll come back to that in a minute. The differences, seeable differences at the face value, what they are. I mean, it's said that statistics have models, machine learning have networks, graphs, but also has models. You have seen Reza's presentation, so Alireza's presentation as well. They have models too, but different kind of models than what we use in statistics. We have parameters, and in machine learning algorithms such as neural networks, Bayesian networks, and support vector machines, they have weights. So simply different terminology and used differently. And we fit models, whereas machine learning algorithms learning from using the training data with certain parameters, then they are applied to testing data set to be able to come up with an explanation and whatever it is. So we have lots of performance measures for statistical model based on some theory, mathematics, hard proof mathematics, whereas in machine learning, we usually don't have that goodness of fit statistics. That's why, as Reza was saying, we are using the test data, and we cannot just go and say, okay, I have this problem, therefore, based on the nature of the data, I can only use this machine learning algorithm. It's not true. If we do have classification problem, there are many more methods to choose from, and neither of them are the best model. Usually we try to apply as many as we could, given our data set, and we choose, again, based on certain accuracy measures, which could be called differently in different textbooks. I mean, sensitivity and specificity is called, okay, sensitivity could be called recall true positive rate in some computing books, but in statistics, we just call it sensitivity. So at one stage, I just went through a couple of textbooks to see what they are, and they are called many different ways in different textbooks. So we just have to be careful of what you are measuring. We have regression classification, and as has been highlighted, then there are many more regression models, and we are improving on them in statistics literature, statistics theory, how we could fit the regression model. You would have all heard about generalized linear models, and then there is generalized additive models, generalized mixed models. So there's many more regression models, not just a simple linear regression or logistic regression. And the classification, I mean, logistic regression is one of the first tools for classification. Banks and health authorities have been using it for ages. And these are usually called supervised learning in machine learning. In other words, they are called supervised because we have an outcome variable, and given the predictor variables, we would like to make a prediction for the outcome variables. Whereas in unsupervised learnings, we don't have an outcome variable. We are simply trying to investigate the patterns in the data. So this clustering, well known in statistics, cluster analysis, which could be hierarchical clustering, which is not very suitable for machine learning data sets usually because they are huge. And hierarchical cluster analysis is lovely, but it works for small data set due to nature of it. But k-means clustering, which can only work for continuous data. I have seen some methods, some articles about being able to use k-means for the categorical data, k-medoids kind of methods. It is possible, but it's a bit tricky. And one of the well-known unsupervised learning tools is market basket analysis. A priori algorithm is really lovely. It's very simple. It works nicely, which could be used, as I said, for unsupervised learning, but also for supervised learning as well. So in that sense, machine learning is borrowing from statistics to do certain analysis like cluster analysis. Unfortunately, when you use the word statistics, you don't get very far by getting the grants. But if you use machine learning, artificial intelligence, this kind of words, you could get large grants. And I mean, this is just a joke, I suppose, by the author of that book. They have meetings in the nice places for both of the areas, machine learning and statistics. It's already been mentioned why traditional statistics is not enough at times, because there are assumptions about the data, normality assumptions, linearity assumptions, independence of the observations is one of the most important ones, where in the machine learning, there is no such assumptions. No assumptions whatsoever. I mean, correlated variables for the predictors is a big problem, as Reza also mentioned. We can't simply use it. It's not just that model might not perform well, but it's also our parameters will be biased if we have correlated predictors. So they will not be giving you the truth. And when you have large data sets, even everything is satisfied and you run your analysis, everything will be significant. So the p-value will be less than 0.05 for most of the cases. So are we really getting the real thing? So if we want to go and find some other way of working with data, machine learning seems to be an answer. And outliers, outliers, are they a problem in machine learning? I mean, depending on what algorithm that you are using, in the decision trees, they are not a problem. But in, say, naive Bayes classifier, which also has some assumptions underlying, like the normality assumption, so there it could be a problem. And it can also be a problem in neural networks. So that's really important with the machine learning algorithm. It's great that Reza and Alireza are showing you how you can use the tools available in our packages, but I strongly suggest you to read through some of the background knowledge as well before you apply, because there are certain assumptions with support vector machines. To be able to get the best results, you really have to be carefully preparing your data for analysis. It's not just about the missing data and things like that, but also you have to scale your variables, because when they are measured in different units, they could have huge impact how the hyperplanes could be performed, or sometimes you won't simply get the best solution. And missing observations. In statistics, usually it's a problem. We try to deal with it with imputations, or we simply ignore the data. Even if we don't, what you have to be careful of is many of the statistical packages by default exclude this information. So you think you're dealing with hundreds of thousands of observations, but if you have lots of variables and simply just because of the missingness structure, you might be excluding maybe 50% of your observations without realizing it. So therefore, you just have to be careful. And also, I mean, missing observations, if it's not excluded in machine learning, because some of the packages, some other software does not exclude them, but they impute them with certain default values. So are we really happy with this imputation method? So therefore, I strongly suggest you either read through the documentation for the tool that you are using to be aware how missing observations are dealt with, or make your own solutions, how you want to deal with the missing observations. And some algorithms simply do not work with missing values, machine learning algorithms as well. So you just have to be careful of it. If it's not working, it might not be you making a mistake just because you have missing observations, and therefore it's not dealing with what's happening. I love R. It's not easy to learn. You just have to invest a lot of time to learn. But one of the things I don't like R is the error messages is not in English. They are in gibberish. If you don't know what you are doing, you will get an error message. You'll never figure out what the problem is, because it's not really simply saying there are missing values, that's why I can't work with it. But it gives you an error message that's not easy to figure out what it is. So what I'm going to do is, over last couple of years, I have worked with colleagues in the health area. I mean, I've been working with them, but I just said, okay, I have been teaching some machine learning algorithms to my students. Why don't I put what I teach to my research? So therefore, I have started in 2014 working with the research problems that was suitable for the machine learning algorithms. So one of them is that related to adolescent depression. My colleagues in one of the private hospitals have a research institute, so I work with them on that problem. So what we have done, and we've also published, you can see that I have 3 papers that I'm presenting. One of them published in 2015, following one will be 2017, and the other one been published just recently, although we've been working on it for some time. So what was the first project about? What we were doing is we went to the high schools and we got approval for it. We wanted to find out, using self-reported questionnaires, stress, anxiety, and depression levels of the students, using a tool called DASS, D-A-S-S. And we wanted to know whether sleep make a difference to their depression, anxiety, or stress. So how long they sleep. And we also wanted to have some physiological factors like omega-3. I mean, we just didn't use omega-3 as how much it's measured in their blood, but we use something called omega-3 index, which adjusts for certain things. In our group, we also had people looking after the nutrition, so they just decided that instead of just looking at omega-3 levels in the blood, looking at something called omega-3 index would be better. And then we've also looked at morning and afternoon cortisol levels in their saliva. So it's not just, as I said, the questionnaire, and there's no other way of currently measuring depression, stress, and anxiety. It just self-reported, answering some questions, but we could easily collect other data from their blood or saliva. I'm proud to say, because we went to high schools, I was actually the saliva collector for the cortisol analysis. So I had to tell the students what they had to do with the little containers. So they had to spit on it. I'm really proud to say I didn't vomit when they were doing it. It was really hard to do that, but it was good to be part of the data collection. So the kids were mainly 16 to 18-year-olds. So we had 444 participants, not badly distributed between males and females. And as I said, we've collected saliva samples, blood samples, and they had to fill a questionnaire so that we could measure their anxiety, stress, and depression levels. So because there is no goodness of fit for the data mining techniques, machine learning algorithms, what I have done is I have applied 5 different classification methods to identify the relative predictive value of each variable, including omega-3 index and sleep and on depression, anxiety, and stress. And the methods I have used was classification and regression tree, support vector machines, neural networks, CHAID, and this C5 decision tree. CHAID is a decision tree as well. It's using a purity algorithm. It's based on the chi-square. Whereas a C5 tree is based on, if I'm not wrong, Gini index. That's what it uses as the impurity measure. And CNR tree uses entropy as the impurity measure. And support vector machine has already been highlighted by Reza. And neural networks is a black box, but I just wanted to see whether it will perform better than the others. But I'd like to highlight here that we wanted a technique that's not just able to predict accurately, but we also wanted to be explain the relationship between the predictors and the outcome, so that some intervention could take place in the future. So a classification model is considered successful when it consistently returns high predictive accuracy rate across 3 categories of depression. I mean, in depression, if I use the scale that was provided with DAS index, I have no depression, mild depression, extreme depression. There were actually 5 categories, but I had to collapse them a little bit so that I have enough number of observation in each category. In the extreme depression, I didn't have enough, so I had to collapse it to the closest category, but it was still the highest 2, so that's why we called it extreme. And the mild one is the middle 2, and there's also no depression category. We have done that for stress and anxiety as well. And what I also looked at is a measure called LIFT, which is looking at the confusion matrix from the predicted values angle, and it's looking at how good the model compared to randomly allocating individuals to outcome categories. In this case, it was the depression categories. I have not used R for analysis, although I used it for pre-processing the data. I use IBM SPSS modeler to run all my analysis. So from there, what did we do? All of these models were applied, 5 classification methods, and I also tweaked their parameters as identified. Different models had the different parameters, hyper parameters, sometimes they are called, and C5 decision tree came to be the best model to be able to predict the depression category for each participant. And here is the result when I include stress in my analysis as one of the predictor variables. So basically, if people are not stressed, or kids, 16 to 18-year-old, if they are not stressed, they don't have depression. Please note that this does not show you the cutoff values for some of the predictors, like we summarized here. We said it's not easy to differentiate between mildly depressed and non-depressed. The reason for that, my colleagues from health area didn't want to go into quite detail, but wanted to get the big picture so that the doctors and nutritionists could use some of these outputs in their day-to-day operations. So if the kids are stressed, depending on whether they are mildly or extremely stressed, they could go into extreme depression or they could go into mild depression. If they could go into extreme depression if extremely stressed. If they have mildly stress, they could go into mild depression if their omega-3 levels are greater than 5.9, but if their omega-3 levels are lower, then they could go into extreme depression. And that was quite interesting because there was no such study before. But of course, you have to note that we are also looking at the BMI here, body mass index, as you know, weight in kilograms divided by height in meters square. And BMI of 23 is just close to the borderline of obese. 25 and above would be obese, 18 to 25 would be normal. So they are normal, but close to the higher border of being close to the obese. And also, if the BMI was less than 23, so we actually ignored here the underweight kids. So I mean, when I say ignored, I mean, we didn't separate them because there are some underweight kids as well at the border of anorexia, but there were only a few of those in the sample, so we don't have to separate them in a group. So if the BMI is less than 23, depending on whether they were female or male, we could come up, we followed through the different decision-making stages. With the females, it was hard to go any further to say whether they'll be mildly depressed or non-depressed. Okay, so it was not possible to do so, but we could, in a sense, give a signal to doctors saying that you have to be careful, they could be mildly depressed, and they might give them some tools to deal with their depression. But for males, interestingly, cortisol was playing some role here. If the cortisol levels were above certain level, then there was no depression. But if they were below certain level, then there could be mild depression. What we also wanted to do afterwards, saying that we have done this analysis using DAS. So stress could only be measured using the survey. So we thought if we didn't use this survey, if we only looked at the blood measures and the saliva measures, how we could go. By the way, these are the results for the that model, which includes the stress. Overall accuracy, 78.8%, and model was accurately classifying non-depressed participants, 99.14%, and 45.65% mildly depressed, and 54.29% extremely depressed. Please note, there weren't many kids that were extremely depressed. So it's really, really important to be able to predict them as accurately as possible. So we were doing a good job here, being able to pick that 54%. What Reza was presenting to you with iris data set, you have to note that that data set has 3 different flowers, but all of them are observed 50 times. And there are 150 observations, sorry, all of them observed, I think, equal times. I can't remember whether 100 times or 50 times, but they were all equal. But in real life, it's not that easy. Like extremely depressed, we don't want it to be as high as non-depressed anyway. We don't want many kids to have depression. And so therefore, it was really good result to be able to predict these kids 54%. In a sense, this model was 6.7 times better than randomly choosing extremely depressed participants. So this is quite a big achievement, and 3.1 times better than mildly, random predicting mildly depressed participants. So it was very good, but it was, as you can see, including the stress. So we just wanted to do something else, and we just excluded stress. We only used things we can measure without using the survey. So the gender is obvious, and also sleep quality came into play here when we excluded the stress, as well as BMI. As in the last 10 years, I suppose, some people argued that BMI is not a good measure of how healthy the body is, but waist-hip ratio could be a better measure. So we also tried waist-hip ratio. We included both BMI and waist-hip ratio in our analysis for both models. But depending on the impurity measure we have used, in this case, waist-hip ratio came up to be the important predictor, whereas in the other one, BMI came to be predictor. What I should also bring to your attention here, how I see that breaking with the decision tree. You can think of it in the normal regression terms, like here, what I have here is an interaction of gender, sleep, waist-hip ratio to be able to predict mild depression. Similarly, here I have an interaction term, gender, sleep, to be able to not nicely predict whatever is happening, but there are some extremely depressed kids over here. So when you going from the root of the tree to the branches of the branches and the leaves of the tree, you're simply following an interaction. In the regression, how we develop the regressions is we usually identify the predictors that are significantly related to the outcome variable. And then we look at whether they are correlated with each other. If so, we can't include the correlated variables for prediction. We usually develop alternative models, including non-correlated predictors. And we can explore the interactions after the main effects are identified to be significant. With the decision trees, even if the main effects are not significant, we are going into and looking at the interactions, we are exploring them. So it gives us a really good measure of exploring all kinds of interactions without thinking about them, because it's all calculated, as I said, based on the impurity measures. Please note here, males sleeping more than 8.5 hours on average was no depression. They're not depressed at all. But if they were sleeping less than 8.5 hours, could be mildly depressed or non-depressed, and we couldn't really differentiate them really nicely. But with girls, you notice that the sleep hours is much less. We're talking about 16 to 18 years old here. So if they were sleeping more, depending on their waist-hip ratio, they could be not depressed or they could be mildly depressed. And if they were sleeping less than 5.5 hours, although we couldn't differentiate them easily with that regression tree, but there were some extremely depressed. So we should be careful of how much they are sleeping when we are assessing. I mean, we're giving the signal to the doctors, to the nutritionists, and whoever caring for these kids, or even the counselors at schools could be aware of that. So in this model, the accuracy, overall accuracy went down slightly from 78 to 72%. Saleha was asking Reza, what should be the value that we should be happy with when we're talking about accuracy? The 100% is best. But if we are getting 100%, what that means is we are having really tightly fit model. It is very good for explaining what has happened, but it's not for predicting for the future, because it's overfitted the data we have in hand. And we don't want really overfitting data. In a sense, I resemble that to custom-made clothes compared to factory-made clothes. Like in the old days, we used to have the custom-made clothes. If I go and they take my measurements, make a dress for me, it will nicely fit on me, but no one else will be able to wear it. Whereas now we are going and buying small, medium, and large, loosely fitting the everyone, but it's fitting many more people than the custom-made ones. So we want a model that is useful. As George Box said, all models are wrong and some of them are useful. We want to find the one that would be most useful. I mean, in one of the articles I read, it was saying that stats is backward-looking, machine learning is forward-looking. Because machine learning is about prediction, whereas statistics is about understanding what is happening. The reason for that, I guess, because we want to change the process. We just don't want to predict what's going to happen, but we want to understand, we want to make changes to the predictors so they impact on the outcome variable, they change it the way that we want it. Like the depression category, we want to be able to play around with the variables, like in here, if we could encourage girls to sleep more, and maybe keep their weight under control, we can possibly move them from being mildly depressed category into no depression category. So we want to make some changes to predictors so the outcome is better. Whereas in machine learning, I haven't seen anywhere that's talking about we want to do that. I mean, although I'm applying the machine learning algorithm here, my idea is to be able to still understand what is happening, not just predict, but also make a change, intervene, and make sure that the best outcome could be obtained. And this model, you can see that much better, 8.45 times better than randomly choosing extremely depressed participants. It wasn't as good for the mildly depressed, but being able to predict the extremely depressed participants is very important in Australia because we have lots of suicide for the young people. We have very high rate. So if we could actually move them from extremely depressed to maybe even mildly depressed, it's really hard to move them quickly to no depression. But if we could work towards moving them the mild depression, we might be able to save lives. So it's really, really important for us to understand what is happening there. And C53 was able to help me to come up with some solutions here. So this study could provide some rationale for prioritizing strategies, how to help these kids to move from extremely depressed category to lighter depression categories, and maybe in the long run, not depressed at all. So that was the idea. That's why we have done this study. If you have any questions before I move to second case study, I'm quite happy to answer questions.
Aisha, I want to say that this was just excellent, but I am embarrassed to say to you that it is 4:55 p.m. here in Lahore. So I don't know how to apologize to you for this, but I have an idea. You've done so much hard work on, preparing these slides in such a good way, and most importantly, in explaining everything in such a good way. So I want to request you that if you have like about half an hour in our next workshop, I will not ask you to be there for all 3 hours, but maybe just half an hour next time, so we can understand the other two examples also in full detail, because then, you know, the impact will be much more as compared with if you would do it now, but in a rushed manner, as you think better. I remember.
Able to, if you let me know when it is, so more than likely I should be able to do it.
Oh, thank you so much. You're so sweet. Yes, I'm so grateful to you. The next one is the 10th of December. Yes, and the next one, four you know, on machine learning. And has been so revealing, and you've done it so well. Thank you so much, Aisha. I'm extremely grateful.
You're welcome. You're welcome.
Okay, thank you. Thank you. So I will share my slides now, and I will then go to the next thing. So as I said, really, really very, very, very grateful to Aisha for such a wonderful explanation and example of application of machine learning. And now I would like to, if I can, go to the next thing. And this is the closing of the workshop. And I would like to request to present you know, Mr. Muhammad Iftikhar, who's the Executive Secretary of ISOS, to present the vote of thanks. So Iftikhar Sahib, would you want me to run the slides, or would you want to do it yourself?
No need to run the slide. I will.
You can run the slides?
Yes.
Okay, then I will stop sharing mine. Let me do that now. Okay. Yes.
Assalamu alaikum. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. Let me first of all start by giving thanks to the Almighty Allah for making today's workshop a resounding success. First and foremost, I thank our special guest, Dr. Aisha Belaghi, Associate Professor at the Department of Mathematics and Statistics, Macquarie University, Australia, and President-elect International Association of Statistical Education, for her keynote speech, who, despite her busy schedule, has found time to be with us at this workshop. A variety of examples provided by her educated us and on various aspects of the role of machine learning in the field of health-related research. I thank lead resource person Dr. Reza Arabi Belaghi and co-resource person Dr. Alireza Safariyan for enhancing our knowledge on machine learning. Machine learning as a technology helps analyze large chunks of data, easing the task of data scientists in an automated process, and is gaining a lot of prominence and recognition. Machine learning has changed the way data extraction and interpretation works by involving automatic sets of generic methods that have replaced traditional statistical techniques. The discourses of both the resource persons and co-resource persons were thought-provoking and highly fruitful, for which both contributors to this workshop deserve sincere appreciation and gratitude, both from PISTAR and participants. Last but not the least, I would like to thank all participants and PISTAR team, especially Professor Dr. Saleha, Naghmi, Habibullah, for their cooperation in making these series of workshops a great success. Inshallah, PISTAR will continue to organize workshops in on important topics in accordance with the requirements of the modern era. Once again, I thank you all of your attention. Thank you.
Thank you so much. Thank you, Iftikhar Sahib. I'm very grateful to you. All right, I think I can perhaps go to my next slide to see what is coming up next. I think nothing other than one more time mentioning my PISTAR team, Mr. Iftikhar, Ms. Professor Muhammad Aslam, Dr. Sharka Hashmi, Ms. Zuleikha Mashkoor, Ms. Kamal Aslam, and the youngest one, Ms. Aqsa Abed. I want to thank every single one of you for being here with us, because without you, there would be no workshop. All the participants from Pakistan, all my dear colleagues from Pakistan, and all the participants from so many other countries. So the formal workshop, I think I should say, is now ending. But of course, prior to that, I must mention one more time that we have so many invited speakers that we had at the World Statistics Day, or those who are going to be our invited speakers in the future. We have right here, I can see Teresita from Argentina. Hi, Teresita. And also, I can see Joachim, your icon I can see. Maybe you can you can open your camera. Hello, how are you doing? Joachim is the current president of IASC. Also, I can see Attila from Turkey. Hello, Attila, how are you doing? You are you were also one of the invited speakers at the World Statistics Day. And I still remember when you said that the statisticians are the driver and the computer scientists are the mechanic, I think you said.
Yes.
And who else? Dr. Ali Hadi, Professor Ali Hadi. Can we see you again? Thank you so much. And all these people who I don't actually know. In fact, I would like to request every single one of you to please open your camera now so that we can have a group photograph. You know, previously we used to stand next to each other. Now we have our icons next to each other. So it would be great if we can have a, thank you very much. So Aqsa and Dr. Wasim, I think you are ready for taking this group photograph. Thank you, everybody. Please do. Professor Aslam, thank you. Dr. Wasim. All these people who have still not opened, Aslam and Raviz, Nadia, Mehtab, Najla, Nida, Shakila, Dr. Shakila, Farhan. Please, let's have some group photographs. Aqsa, I hope you have taken some. Thomas, how are you doing? I can see Thomas now. Who else? Dr. Kulsoom, thank you very much. Travis, thank you. And Mehnaz, Ms. Mehnaz. Who else? Please, everybody can, I think, allowed to take your screenshots. I mean, every one of us can do that. Aslam, I would like to have a look at you. There's some names which I can't read fully. Farhan Sahib, thank you. Muhammad Abbas, is it? Can't read the full name. Dr. Sharka Hashmi, finally you have arrived after all that electricity problem. I'm glad you're here. So thank you, everyone. Thank you so much. I think this has been great. And once again, I repeat that all these, this workshop that we've had and this wonderful talk that we've had, it's the result of, you know, so much effort on everybody's part who did it for us. So I now, after just 5 minutes over time, want to say that inshallah, we will meet again for the third level 3 of this workshop series on machine learning on Sunday, 10th of January, 2021. So happy new year also to everybody. Let's hope and pray that the next year the world overcomes the problems associated with COVID-19 as I'm a Muslim, of course, I say that with the help of Allah subhanahu wa ta'ala, let's hope and pray that the world gets rid of this problem. And my prayers for all those people, and of course your prayers too, who are suffering at this time because of this problem. So inshallah, we will meet again. I'm going to close this, but after that, I would like everybody to stay here for as long as you like, so we can have some informal conversation. This is the close of this workshop. Thank you very much, ladies and gentlemen.